what we're going to be going over here is a linear programming example where we're going to be allocating manufacturing resources to optimize profits and minimize costs. And what this is going to include is resource interdependencies or reciprocation. Okay, so what we're going to be looking at here is the marginal cost that we have to come up with to decide the best product mix. So the data that we're going to be working with here is where I'm going to have, let's just look at it here, we're going to have some material costs represented by M here, and that's going to be at $10 a pound. We're going to have some labor costs, L's here, represented by L at $26 per hour, and those are all variable costs, and those are what we're going to be allocating. And then for this problem here, we're going to have some power cost represented by E, or electricity, let's just call it, and then we're going to have some repair costs here, or maintenance costs, represented by R, our variable here. And those are what we're going to be looking at as our service departments here. We're going to have that reciprocation here to determine the marginal cost for those different costs here for power and repair. And again, those are variable here, but they're going to be interdependent. And I'm showing here we have a fixed cost of $10 per hour plus so much here, $1.80 per kilowatt hour, and then $5 extra, $5.20 here per hour here for the repair cost. So we got a fixed portion here, and then we got this variable portion here that and this is what we're going to be working with in this problem. And then you also would have some overhead here, and I'm just showing $100 here, but it's all going to be fixed overhead here, and it's not affecting our linear programming here for determining our levels of our different products here in material, labor, and so forth. So you omit that from your linear program. And then for our sales price here, we're going to have two different products, P and Q here, and we're looking at different sales prices, but I'll just use here for our first example, we're going to look at as $80 for P and $66 here for Q. And then we're going to have product P and Q here. They're going to have some usage here for those direct labors, direct materials. And then you're going to have machinery hours here as well, that machine A and machine B that those products are going to go through, and there's going to be some usage there. And this is what we're going to be looking at, this power and this repair here. There's going to be usages here, and those are the demand constraints. And I'm just showing them on a unit basis. And the other thing we have that we're going to be looking at is those our machine A and machine B for our different products here. We're going to have the capacity, or the machine hours that are available here for machine A at 150 hours and machine B here at 50 hours. So this is going to be our supply resource constraint here, whereas these demand, or these unit usage requirements here are demand constraints here, and we'll look at that. We'll be setting up our program based on these numbers here. So the first thing we want to look at is just setting up that objective function here. In this case, what we're trying to do here, we're trying to determine the maximize the contribution margin here when we're looking at it in terms of our optimizing our profits here and minimizing our costs. So we're going to be looking at it in terms of contribution margin, and that really takes your revenue minus your variable costs. So just looking at our objective function here, total contribution margin, where we're going to be maximizing it, we'll just take $80 here, and that's that sales price here for product P, plus 66 here for dollars here for Q, times Q, $80 per P. So that represents our revenue, and then we just have to subtract out our variable costs. And we're going to have what, $10 a pound here for whatever material we're using, represented by M, less $26 an hour here for our labor, and then $1.80 here for the electricity or the power that we're looking at. And that 1.8 here is really the variable portion here. Remember, there's a fixed portion of $10 per hour here, but we're only concerned with the variable portion here. And also for our maintenance here, or the repair cost here, we're going to be subtracting $5.20 here times whatever repair hours we have here. And again, these are just the variable portions for each of those. Remember, there's a $10 per hour fixed charge. But when it comes to linear programming, we're not going to be concerned with the fixed cost at this point here. And this is where we're going to have that reciprocal, or the marginal cost that we're going to be coming up with for the power and our repair costs. So this is going to be a critical item here. So what we're going to be doing here is we're going to be using the marginal cost here to decide the best product mix, and that's going to include this reciprocal relationship here between those service departments, the power being applied to the, in this case, the plant that we're looking at, and the repair cost or the maintenance cost for the plant that we're looking at. So what we're going to do here, we're going to be factoring that marginal cost into the profit equation that we have here. So we've taken those marginal costs for material, labor, and then our power here and our repair costs are into, and we look at it in terms of contribution margin here, not profit, but just contribution margin when you're looking at it in those terms. So the question we're going to have is how many units of each of our services here, that power and our repair here costs, are going to be used to produce 1 unit of each of the outputs here, products P and Q. So ultimately that's what we're getting down to when we're looking at our marginal cost here. So we're going to use the power E here, and really what we're going to look at that relationship here. The power E here is an increase, or it increases our repair activities, and our repair hours R here increase our supply of power E here. So that's going to be that relationship or reciprocal relationship that we're going to look at. Okay, so let's go and look at that. Okay, so I've got it laid out here off that demand constraints here. And what I've done, we're going to be just looking at this interdependency between power here and our repair costs and how we factor that into our linear program. So what I've done here is I've got our provider of the outputs, or our supply I'm showing here for machine A, B, material here M, labor L, and then power E here. Really, that's electrical cost, and then our repair R here, our maintenance cost. So just laying it out, and that's what our supply is here, and then the demand or the consumer of those inputs here, and that's our demand showing across here for P, product P, Q here, and then electrical, repair, and then material and labor. And really, for P and Q here, it's pretty easy to come up with. Just come off the demand constraints here, and I've got it shown here on a unit basis for each of those, machine A through repair R here, on a unit basis for P and Q here. Okay, so that's what we're going to be using in our linear programming here. I won't go over them. You can go refer back to those numbers if you have to, but it's on a unit basis here. But what we're going to be looking at is we're going to look at the supply here, power E, for electricity, we'll call it, and then repair R here. So we know what they are for P and Q here on a unit basis, but this is where the interdependencies comes in, and that's really the demand here. So look at it in these terms here. And the reason, and first off, before we get into those numbers, understand it here. It makes good common sense because you're trying to come up with your repair costs, and you want to allocate that to your product here. And you also want to come up with your power cost and allocate it to your product to determine the contribution margin in this case here. Or you want to be able to come up with some variable costs or marginal costs on a per unit basis to determine the ultimate product mix is, and it really includes both power and repair, and this is where you're going to have this interdependence. And it makes sense here because you use so much power in the factory here, and you use power to power the machinery, the equipment, and everything. And based on the power usage here, the more power you use here, that is, the more your machinery runs and so forth, the more repair costs you're going to have. So that's the interdependence you have here. And based on some statistical, maybe regression analysis or so forth, we come up with some sort of relationship here between our power and our repair here, and that's what we're going to look at. So for our power E here, let's look at our little matrix here. And just to make another point here before we get in, material and labor here, there's no interdependency here. It's just zero here. But we have this interdependency here between our power E, let's look at it, our supply here, power E, and then the demand here. We also have a demand for E that you have to set up in your linear program here. So we're going to have 0.1 here. It's going to be looking at our demand, and we'll go and look at that. So this 0.1 here is really saying this. E here, the power is supply, and the E itself here, the power is demanding 10% of whatever electrical power is being used by the plant here. So you have to set that up here to come up with your linear program here. So your demand, your power, your supply here is also being part of your demand, 10% here for E. So that's where you get that 0.1 in. And you want to work with a unit basis here, 1. So I'm just converting the 10% over into 0.1 here. And then for power E here, the supply, the repair R here is using 0.2, or in this case, 20%. So R here, your repair costs are demanding 20% of the electrical power here in the plant here. That's the interrelationship. And then we also have, maybe I should have went over this here, the E, and then we have that E here, our repair, our supply here is 30%, showing R here. The supply is 30% here, and the electrical power is demanding 0.3 or 30% of the repair here. So that's what come up with a relationship. So here's our supply for E and R here, and here's our demand for E and R, that interdependency here. So you have to come up with some percentage between those two. So really you're looking at a ratio here, a ratio as a unit of 1 here, some percentage you want to come up with. So that's what you have to come up with here. Okay, so we've got our in demands here versus our supply here, and then we can go in and we can put that into our linear program here. So we come up with our objective function here that I'm showing here, and that's going to, and let's look at how we come up with our maximization problem here for this linear programming. And this is where we have to come up, we got our objective function here, so now we just have to set up our capacity constraints here, and that's really looking at the demand here for each one of those variables, P, product P, Q here, and then we also have material, labor, and then our power, E, or electrical here, and then R here for the repair costs. So then we have our resource supply shown here. So let's just go and look at that. So just taking those right off our consumer inputs, if you went up there, you see machine A here, P is using it's taking 1 hour of P. From machine A, P is using 1 hour, Q is using 1 hour. And in machine B here, P is using none of that. P is using none of machine B. It doesn't go through machine B, but it uses, but Q uses 1 hour here in machine B. But then we have our resource supply constraints setting up here. So for machine A, we only have 150 hours available. So our function here for our linear program has to be less than or equal to when we set it up. And then for machine B, we only have 50 hours here. So those are our machine hours. That's our resource supply here as you look at it. So that's less than or equal to as well here for machine B. And then the material here. Material, labor, power, and repair. So this is the key here. You want to set up, or you have some inequalities here, less than or equal to, and you have some numbers that you're looking at. But let's just look at, in linear programming, what you're doing is you're just converting an inequality here, that less than or equal to an equal to. And we'll look at it just in some common sense here, just understand it. So what we're doing here is you have your material and your labor here, and power and repair require on a unit basis for product P and Q here, and we don't have to go through those. But what we want to do is this here. In that equation that we have up here for our material, labor, electrical, and repair here, those are the variable costs, and we're subtracting it from our revenue here. So what we want to do is we want to use only the amount that we actually need here. We don't want to be using any more of those variable costs as we need. So to do that here in your linear programming is you have to set up your inequality here and just make it sense here. So what we have is, remember, for material and labor here, and let's go through them first here. So for what you want to do is you want to subtract out here your usage, your demand here for P and Q on those on a per unit basis here. You want to subtract 1 times whatever material you're using. So you want to come up with 0 amount here by just subtracting whatever unit basis here, whatever material you're using here, you want to subtract it from the material or the demand that you're using here for P and Q. So you're going to subtract out 1 here for your material in your equation here, and you set that up as a variable here. And then for labor, same thing. Whatever labor you're using, you want to subtract all of that labor cost out here. So you're setting that equal to 0. So that's really what, and we'll look at it, you may look at it in terms of a diagonal here for your linear programming if you're familiar with that here. But then this is where we get down to our power and repair because of that interdependency here. So looking at our power here, okay, this is where it comes in. So what we want to do is, for the power, we want to subtract out 1E, or that whatever power we want to subtract out from it. But what's sitting here in that equation is that 10% here. So if we, to get our equality here, to bring it over here, we subtract 1, a unit of 1 from 10%. So we're going to get a minus 0.9 here, or it'll be like 90% here of E here. So that's all we can subtract out because we're leaving in, leaving in that, we had that 10% sitting here. But for our repair here, we're just going to, since that's sitting here in a power E, we just add that in here, 0.2 here. Remember that was that repair, that 20% here. Just add 0.2 times whatever repair, and again, that is equal to 0 here. But that relation, that's where that interdependency comes in here, just so you understand what's going here. You leave in that R, that 0.2 here, or 20% here, but you subtract out 1, minus 1 here from whatever you had in your E, that 10% here. So that gets you 0.9. And then your repair costs here, of course, you know what for P and Q here, but this is again that interdependency here. So for E, remember we had 30% in here. So you just leave that into it here, but then you subtract out all of that repair cost that you're having here, minus 1.0 here. All right, you see that here. So there's where you set up, you really converted here inequality equality here by subtracting out 1 of whatever supply of power you're using, but you had 1/10 sitting in here, so all you have is, now you just can subtract out 0.90, but then you also had that 0.2 tenths hour here for repair. You leave that in here, and then for again your repair here, you leave in the 0.3 here, E, whatever you had here, because of that 30% interdependency here. But then you subtract out all of that R here. But this is how you have to do it. Just remember here, you're going to have your equations here, your supplies all shown here, and then your demands here. So you set up your variables in your linear programming, however you want to do it. But I just put in P, Q, M, L for labor, E, and R here, and just drawing those arrows down. Those are the coefficients that you're going to put into your linear programming for each of your demands here that you're showing here. So those are really the coefficients, and I'm showing them here, but that's how you'd set up your linear programming. Okay, so now let's go and we'll solve this problem here and get into some depth here on how we come up with marginal cost here for that power and repair, and also our other costs for material labor, and also those machining constraints, how they figure into our optimizing our, minimizing our cost and maximizing our profit. Now for our linear programming solution, and we're going to look at two different solutions. We're going to look at maximizing our profit or contribution margin versus minimizing our marginal cost or the cost of capacity. So for our maximization problem, really we're trying to determine the optimal product mix here. And with our minimization problem, this is where we're looking at when, where, and what cost it takes here to expand any capacity if you have to do so. Okay, so we've already set up our problem here for our maximization problem, or what they refer to as our primal problem here, and we have our capacity constraints here, and we have our objective function here. So we want to transform this into the minimization problem, so we'll go through and do that. So we'll start out with our objective function here and look at all those different coefficients that we have here in our max problem here, our primal problem, so that we can convert over into the minimization problem. Let's go and look at it over here. And what we do here is we take those coefficients from the maximization problem for the objective function, and they move into the constraints here on your minimization problem, or what they refer to as the dual. Those coefficients with their signs move in as constraints here. And remember, in our maximization problem, there was less than or equal to. Well, we converted it over to greater than or equal to here in the minimization or the dual problem. Okay, so that's first for our constraints here in our minimization problem. Now let's look at our objective function, how we determine that. So we go over to our max problem here, our primal problem, and we take those, our resource supply, those constraint coefficients here. In this case, we only got 150 and 50 here. They become the objective function coefficients here. And this is where we're going to minimize our total cost of capacity, TC here. And that would be what we want to look at. Let's go and look at that here. So for this 150A and 50B, if we go back over here, you can see that is row for machine A here is for that 150 machine hours, and machine B here is for those 50 machine hours here. So those become the coefficients here in your minimization problem. 150A plus 50B. So that's going to be our objective function here, and that's minimizing the cost here of machine A and machine B here. Okay, so that's for our both our objective functions here and also our constraints here in the minimization problem. So now let's go and let's do our conversion here for, in this case we call it opportunity cost here. We're really moving our columns into rows here. So going back to our capacity constraint problem here, I've got the different columns that we have laid out here, P, Q, and so forth on here. So starting with our first column here, P, and you can see all the coefficients here for P for those variables, machine A here through all the repair costs or repair R here. All those coefficients here for the first row or column here become, let's move over here, they become the row coefficients here in your minimization problem here, and that's for, remember that was those coefficients were for product P here. So again, just make sure you get all your, the computer will do it automatically here in your software package here, but just so we understand it, make sure your column coefficients here are laid out as such here, P, Q, M, L, R, and or E and R here, the way I have them set up here at least. So those become, that column here now becomes the row here in our column in our maximizing problem becomes the row here in our minimizing problem here. And also just remember it's greater than or equal to here. And if we move, let's just go through the, so that was for P here. Let's just go through for Q. Same thing over here, Q in our primal problem or our maximization problem. Those coefficients here for Q, all those Q's here, let's move over here. For our problem over here, the minimization or our dual problem, that product Q becomes the coefficients here for each of the columns. So we just columns in our program here. So all we did is we moved our column from our max problem into the row here for our min problem. And if we just gone back here, you can do the same things here for M and L. We won't go through those here, but you just get them in line here. Just make sure you get the right coefficient names in here. But then we get down here to power E and repair R here, our rows here. Well, let's look at for E here, that column. Let's move, and then for R here, that column here. And we'll move over into our minimization or our dual program with that, so you can see here. So for our column here for power E, remember we had those coefficients here in our column was 0.9 here and 0.3 in the column here for power E. They now become, again, minus 0.9 here plus 0.3 here. So that column for E in our min or max problem becomes the row here in our for power E in our min problem. And the same for R here. That column here in R now becomes in R in the max problem becomes the row here in the min problem here. Just so you keep all your, if you're working with those different coefficients here, just so you keep them straight here. Okay, so that's our problem. Okay, so now let's work off our minimization problem here and understand what's going on. So this is what you're going to do here. With these greater than or equal constraints here, this is where you're looking for a shadow price or a due price, and that really gives the cost of meeting the last unit of the minimum production target. We use that minimization problem here to determine our production target here. So that's really looking at the cost of the additional unit for each of those different variables that we're looking at. And I've done it here, and this is the solution I came up with here. Just put it into your linear program. Our minimum cost comes up at 500 here. And that was based, this is minimum cost here for our minimization problem. And then I got these different solutions here. Okay, so let's go and understand what our coefficients are, what our cost constraints here, what they're really talking about here. So if I just, first off that program, if we went and looked at here, the linear program gave me the marginal contribution margin for each on a unit basis here for a 4 and 2, and let's look at those up here. That was for product P. The contribution margin here on a unit basis was for product P was for 4, and for product Q was 2 here. So that's the cost here of that last unit. That's what it's adding to the contribution margin respectively for P and Q here. But the other items here, now This is our, really what this is, those our dual price or those our shadow price here. And those are the variable costs that we have here for each of our, for our material, our labor, our power here, power E, and repair cost R here. We have those coefficients that we brought over from our objective function here, but really what they're telling us is this here. We're really solving two different sets of equations here. For material M and L, or labor L here, it's pretty easy because just the solution, you can see it is M here equals 10 minus 1, minus 1M minus 10 here for your constraint. So that's your variable cost here for material, for that unit, that last unit of material that we used here based on a minimization problem. And then L, very simple to solve it. You get a 26 here. You had 1L minus 1L minus 26 gives you 26 here. Okay, so that's what the linear program did here. But this next set of equations here for power E and repair R, those are as two sets of equations here, two equations, two unknowns here. Really, that's what it's telling us. This is that we're going to have a variable cost here for our power E here, our E variable at $4 here, and our repair cost here at $6. So that is our dual price, or what they call our shadow price. And really what all that is telling us is here, we've got to earn more. If we put in a material, the labor here, and the power and the repair cost here on a per unit basis, that we have to have a benefit greater than those costs that we have here if we're going to add any more capacity here, produce any more product, if we've got some constraining amounts here, which I didn't get into here. But nonetheless, that's what it's telling us here. And just by solving your linear program, minimization programming here, you're going to get, in this case, we have that added contribution margin for both product P and product Q on a unit basis shown here. But what is really key is those variable costs that we're looking at here. Okay. So that's really got two ways. Just put this in here, go through your linear program, minimization program, and it's going to give you all these values that we have here. Or, just to make some sense out of it here, we can go down and we'll just look at solving those equations. So we'll look at we looked at solving this set of equations here, very easy. But what about those second set of equations here? Okay, so what I've done here, I just put it into my, you could do it by hand here, I just put it into the computer here, and what did I come up with? E is equal, our power cost here is $4 or 4, and R on a per unit basis here, and our R or our repair cost here is $6. And if that's just solving these two equations, two unknowns that we have up here. But if I gone up to my linear program, I'm going to get the same results here for when I put in that just a linear program. What I got, $4 here and $6. It's Z5 4, Z6 6 on those variables here. Okay, and really what you're talking about here is just putting it in perspective here. Remember when we talked about that electrical power cost, it was $10 plus $1.80 per kilowatt hours here, and a repair cost was $10 plus $5.20 per hour here. But these are our marginal costs here. We weren't working out what we're doing with this linear program. We were trying to get this power and this repair cost into our marginal costs here. So we could predict our product levels more accurately here when we put in those marginal costs, rather than just work off these functions that we have here. And then one other thing here, when we talk about that reciprocal relationship here, that remember we looked at that matrix here with that 10, 20, or that our supply here based on a percentage here and the demand based on a percentage here. Really what you're doing, if you would do this by hand here, and we're not going to go through it all, you're just taking an equation here for E, your power or electricity here. You're just taking $10 plus whatever you have in your matrix here. In this case, it's 1/10 or 10%, 1/10 E plus 2/10 R here. And then you got your R function here. It's just $10 here. That was that hour here plus 0.3E here. What you're doing here is just you're just putting one of these factors into the other one here. Whatever E equals here, you put it in there to determine what your R or your rate is for R here, and the opposite would be true here. Just to explain what we're talking about with that reciprocal relationship. But we did it here with our linear programming to put that cost in here so we can determine what our product mix would be based on the linear cost here using a linear programming. And then one other thing here, going back to that, this is our primal or our maximization problem here. This is where you have that less than or equal to constraint here. This is again, to understand, this is where the do price gives the value of having one more unit of resource, or the profit of adding an additional unit here. The minimization gave us the cost of an additional unit here, but this gives us the profit of an additional unit. So what I've done here, all I've done is I've looked at, just to understand what we're talking about here. Remember that our unit resource of those machine hours here. What I've done here, I'll just take and in the program here, I'll just say this is 150 hours, and then for A here, 50 hours for B. That's what we're sitting at with our constraint here, and we come up with a contribution or a contribution margin of 496.8 here. Well, with the minimum problem, cost problem, I come up with 500 here. Just make sure that they are the same here. So this one is 500 probably. In that solution, it just rounded it off here, or that's what it come up with the linear program minimization problem. But with the maximization problem, same thing, 496.8, very close. And then what I've done here, just for that unit resource, this is where you want to vary it here. So for the case here where I added an extra hour here, remember we talked about that due price gives the value of having to add one more unit resource. So I've done that for our machine B here. I just put that in at 51 hours, machine A at 50, and I come up with the contribution margin now moved up to $501. So we have, from adding one unit here of hours here to the B machine, we have a contribution margin increased by 4 here. And that's pretty much what we got in our minimization problem. We're looking at 4 units and 2 units here. And then I look at the case here where we've gone from left machine B here at 50 hours and moved machine A up to 151 hours. This is where I got the contribution margin here at 499.6. And really what we're doing is we're comparing it to the base amount here, that 150 and the 50 here. These are just by increasing or giving that extra unit of increase in our unit of resource here. And I come up with the difference between 496 and 499 here was contribution margin of 3 here. So it's all pretty close here when we're dealing with looking at that minimization and maximization problem. And then one last thing here, what I've done here, just to get an understanding, this is sort of sensitivity analysis to understand what's going on here. And I looked at the range of the optimality here. Okay, before we get into that, just understand here, when your program gives those, you're going to give your power, your labor quantities, your material quantities, your repair quantities, you'd have to put those back into your objective function. But for your power, let's look at that power, and that's repair, and understand what's going on here. So for your power, whatever number you're getting here, in this case I got E at 300. Remember, we had a factor here of $1.80 here. So you'd have to take that extra $1.80 times that 300 here to get your power result here. And then for repair, well, we got 342 here. You'd have to take that times that quantity of extra quantity amount we had at $5.20 to come up with your repair cost. Just understand that. And then for this range of optimality here, just taking that objective function or maximization function here, what I've done here, I've just left my Q here at 60, a price here of Q at $66, but I looked at the price of P here. I started out with $70, and then I incremented $71, $72, all the way up to $80. And what had happened, of course, my range here, contribution margin, increased from $494 up to $499. But the inflection point is this. At $70, I was producing 0 P here and 50 of Q. But it wasn't until I hit $80 here in my price for P where I come, now I just move from P from 0 up to P 101, or it should be about 100 here, but nonetheless it rounded up to 101, and my Q is at 50. And this is what we were dealing with here for our problem here that we're looking at. I looked at a P at 100 and a Q at 50 here. And then up until 80, then I go 80, 81, all the way up to 86 here. When I got to 86, of course, your contribution margin is increasing for 499 up to 1204, but I didn't change any P and Q here. They stayed the constant here until I hit 86. At 80, I had a P of 101 here units, Q of 50 units, but when I got to 86, that's when an inflection point worked here. That was in change here, where P, I've gone from 100 up to 151, and Q went from 50 down to 0 units here. Just to understand that. So that gives you the range of optimality. So the idea is here, you get, when you're talking about P and Q, you can look at these different quantities for each of those different products here, but you see what's going on here. You increase your contribution margin here, but you're not changing those quantities until you hit different inflection points. And then your quantities between product P and product Q changes here. Okay, so that'll summarize our problem here, but we can go look at it in a 3 dimension here, get a little perspective here on the layout of that if you're looking at it, trying to determine those minimization and maximization problems, looking at it in a graphical form. Okay, just now looking at this solution here graphically, and we'll just look at it in terms of this range of optimality here, where we had those different inflection points here between P and Q. Okay, so first off, looking at it down here in a 3D plot here. So when you're plotting these out here, because you have all those different constraints and variables, it's pretty difficult to plot here. But just using your computer software package, what you would do here is just plot your P versus Q, product P versus Q quantities here. So you'd have along your axis here, lower axis, you'd have your product Q here, your quantities increasing here, and P quantities here. So what you would do here, and then those other constraints would be located on some plane here. So that's what you want to look for, those different constraints. And what you're going to have here is where you can bump up against some constraints, those you want to check here to make sure that you're up against your constraints and that you're using all your capacity, or looking at what constraints are causing you problems or you can't produce any more products. So just looking at this first one here, we had that contribution margin here shown on our x-axis up and down. We have at 500 here. This is where we were actually producing P at 100, quantity of P at 100, Q at 50. And you can see here we're meeting some of our constraints. Those black lines here are constraints on this colored plane that we have here. Okay, and then if you look at it over here in 3D, you can see sort of the same thing. I got this shaded gray area here, but you can see here this is your profit plane here, and then you've got those different constraints here that you can see it sort of a slicing through here in 3D at that point here. Okay, then if you go down here and then looked at that other inflection point here, this is where P equals 0, producing no P's in Q. We have 50 units here. You can see that we had a contribution margin of $294 here. Okay, so you can see you got to check what constraints you're up against here. In this case, I don't see some constraints here, but I don't see that we've met any of these constraints here. We're not up against that one. Okay, so that tells you something here. And then if you go and look at the other point here where we had P at 150, Q at 0 here, so you can see that this is our contribution margin here, $1,208 here. You can see we're up against some of the constraints here. If you look at these brown or these black lines that are on our profit plane here, just to get you a different idea here of what you're looking at when you're trying to determine any of the constraints and see if you're up against them. So a graphical package can work here if you have a means of graphing it, but you can't really do it by hand here when you've got all those different variables. When you're graphing by hand, you can only work with two variables, x and y, essentially. Okay, so that'll summarize our discussion.